Example, specifically this Power Rangers example. But, oops, sorry, PowerPoint here. So we've been talking about effect size and confidence intervals as other ways to describe a point estimate. So confidence interval is around the sample mean. It gives us a range of scores to believe in. And the effect size tells me how much I should care. All of that kind of taken together plays into power. So power is the ability to reject the null, given that the null is false. So kind of a reminder, if this is like the truth, so the null's false, null's true. We drew this box a couple chapters ago, but coming back to it. This is our study. We say it's false. We don't say it's false. Power is here, the ability to reject the null when it's actually false. I think I flipped this from last time, but it's still the same table. If the null is actually false, and we should reject it, and we don't, okay, that's type 2. So we missed it. Okay, that's theta. So I missed that the null was false, and I didn't reject. If we reject the null and it's actually true, and we shouldn't have rejected, that's type 1. That's alpha. Remember, the first mistake is the worst mistake, saying something happened when it didn't. So this is I would reject and I shouldn't. This is don't reject and you shouldn't. This doesn't really have a name. This is just like a correct decision. But it's kind of sad because the null isn't true. So the null is true and you didn't reject. I mean, you made the right choice, but basically your hypothesis is correct. So we've been talking about how do I deal with type 1 error. That's where we're setting p less than 0.05. When I said, remember, think about that as alpha, that's what we've been talking about. So that's the likelihood we're going to reject the nulls when we shouldn't. That's why we keep it really low. So null hypothesis testing is kind of backwards because we want a small probability, and really that's because we don't want to reject when we shouldn't. That's why we use small p-values instead of I'm 98% sure this happened, that sort of thing. So power is the ability to reject the null when we should. So you think of power as like, how likely am I to find something that's there? You can think about this in a like police detective sort of way. I think of it as a magnifying glass. So how likely can I find the thing I'm looking for? It's like a Where's Waldo. It's opposite from beta. So power and beta total to 1. We tend to set type 1 as a probability of less than 0.05. We tend to set beta as 20%, because we're okay with missing things when we shouldn't, or we're not okay with lying, essentially. So we find beta to be more acceptable, and that makes power 80%. Okay. So these two across here add up to 100%. So in theory, this one is 95%, this box. So it's the probability we're going to avoid type 2 because they are opposites of each other. So we don't want to miss something, but we're okay with missing something more than saying something is true that isn't. So we're going to work this silly example, this Power Rangers example. So we're studying the effects of Power Rangers. We still in the Power Rangers generation? Do I need to change my example yet? Okay. And so if the population score is known to have a mean of 80, standard deviation 30 on this imagination scale, we grabbed people who watched Power Rangers and we're expecting them to score higher. They're giving you an intended sample of 5 participants, which we already know is kind of too small, and average score is 120. So we're going to figure out how to calculate power. We're going to do this once by hand and then once with the script. So the first step really is what are the numbers I need? Okay. This is totally separate from the hypothesis testing steps. This is just listed as steps to keep you headed in the right direction. So I said the population mean is 80. Population mean is 80. The sample mean that I'm expecting is 120. So mean for my sample is 120. I said I was going to test 5 people, and the population standard deviation is 30. Okay, all of that is on the handout. So we're expecting to test a sample of 5 people, and I'm expecting this to be 120. So the purpose of power is often to make sure that you have enough power to run your study. So we're going to calculate what's the likelihood of them rejecting the null here. Because I have more than one person, I need standard error. Oh, calculations. Okay, so I got 30 divided by square root of 5. It's 1342. All right. The next step, so this is just basically write everything down that you have. So the next step is, what is my critical z-score? And this was probably the most missed thing on that quiz. But on this particular one, you do have to pick a side. So really under step 2 here, it should say pick a side. We're not going to do a two-tailed power test because that just gives everybody a headache. So we're going to talk about doing one-tailed test. Because I think if you just get the idea, this is the only time we'll do this by hand. So we've got to pick a critical z-score. So we're going to go with probabilities less than 0.05. That's alpha. Right? Type 1. That is not p found. That's the hypothesis testing part. And if my expected mean is 120, we're going to pick positive. Right? So we expect them to be up here. I'm going to try to do, how do they do it in the book? Yeah. So this is the sample, and this mean is 120. Pretend this keeps going. All right, so I'm trying to draw this like the book does. So if I'm expecting the mean to be 120, I'm going to pick a positive test. So we're going to say this is a positive tail test. So what is my critical z-score if I have 0.05 and a positive test? So I can use R for that. This is all later, all of these steps. But it would be Q norm. Right. Sorry, let me make this bigger so you can see it. So we got Q norm. We've got 0.05. Lower tail is false because I want the top. Okay, so 5% at the top. Should get 1.64, and I do. So my z critical is 1.64.
And will that always be true for power tests that it's going to be 1.64? If it's one-tailed.
If it's one-tailed and it's 0.05. If it's 0.01, it'll be 2.33. Okay, so generally what we've been doing as part of hypothesis testing is picking z, right, that's step 4, and then step 5, converting our mean to z. In power, we kind of do it the other way. So we find a z and then we go back to x. So this step is actually not different than calculating the confidence interval. That's what all you're doing. It's also basically calculating x. So it's the mean plus standard error times z. So I'm trying to figure out if I have a z-score of 1.64, what does that mean on my raw scale? So my raw score is going to be the 1.64 times standard error, which is 1342, plus 80. So we're going from z critical to an m needed. So I need 102 points to reject the null. Right? So everything out here is reject. Now, sort of right away, it's going to be clear that 120 is going to be a good score. So essentially what we did was I took 80 and I said, okay, 5 samples of 5, how big of a score do I need to meet the cutoff? This is actually what you've been doing, right? What's the, like one of the quiz questions was, what's the score for someone who wants to be in the top 10%? This is that. Okay, so what's the score for the top 5%? That's 102, and we have 120. So we are well past the cutoff score. So I would be able to reject the null, but that's not the point at the moment. We're trying to figure out how. So I can reject, but how likely am I to reject? So now the question is, how far away from the mean am I? If I need 102 and I have 120, how far away am I? So this part's effect size. How far away am I? So we're going to calculate this distance here. Here's my sample. But we're going to do that in z. I'm going to take my mean needed, 102. In the last step, my sample mean, 120, divided by standard error. So not quite effect size, because standard error is on the bottom. Okay, so 18 divided by 1342. Okay, it's negative 1.34. Hold on to the negatives. So what does that negative mean? The negative mean, that negative here, implies, not to use the word mean, that the mean that we need is less than the sample, and that's good. So the score that you need, you have a higher score, which is what you want. It's very tempting to reverse them, because I have 120 minus 102, so I'm 18 points ahead. But remember, we're trying to figure out how much above this we are, so we actually want a negative score. It's kind of backwards. What do we do with this score? Well, we take that, stick it into P norm. So I have got P norm, negative 1.34, still lower tail false. So if once you pick a side, lower tail true or false, stick with it. So we should get 91% if I round up. Does that make sense to have 90%? Yes. Okay. Because what that means, and if I had drawn this even better, is that there's 90% of a difference here. Right? So this thing. That does not look like 90% on this graph because I'm not good at drawing these. But I have a 90% chance of finding it, if it's actually rejectable. And it's, to me, like the number should be big because I'm way above the score I need. If we're way below the score we need, then the number should be really small because we've missed the mark. Yeah.
What will the number be if you like exactly hit 102? Like mathematically, how does that work? Like if you had exactly hit, would it be 50%?
The mark.
Like exactly 50%?
I don't know.
Because
Let me see. Yeah.
Yeah, it makes sense.
Yeah. Power to me, I'm always like, hold on, I have to calculate it. But yeah, so if you hit right on the cut up the critical score, yeah, you have about a 50-50 chance.
Of rejecting your null once you conduct the test.
Okay.
Yeah, that makes sense.
Because if you expect a mean of 102 and you miss it, you might get a 101. So that's the idea. So these are all expected scores. The population is what you know, but you're expecting a 120, and I'm expecting to use 5. Okay. So let's actually just use this R thing now, because this will lead us into the next part. So ignoring these 2 lines that I added at the top, what I've got is a script that takes all of this and just calculates it for you. So what you've got is the population mean, population standard deviation. That's these 2. Your expected in alpha, which is 0.05, could be 0.01. Be sure you're reading the question. My expected sample mean, which I just changed to 102 to answer this question, and whether or not I want to go lower. So the cool thing about this code down here, this calculate, is that it is dynamic, meaning whatever you change up here, it auto-calculates down here. So you actually never have to change anything here. Don't touch this. This is the MC Hammer of your code, right? That joke probably is not going to work, but I can try. Up here is where we're going to change. But what that allows us to do is to test some ideas here. Okay. So these are the steps. Okay. And if you have questions on this, I'm teaching Rachel and Shannon how to do this tomorrow, because it's been a long time since they've had to do this by hand. But they will know how to help you out. Okay. Let's say, what did I do first? So we did this one, where we calculated power was 90%. So you can fill in this first box down here. So it was 90, 98. Let's see what happens when we change some of the components. And I'll work this again. So let's try increasing the sample size. Because 5 people is kind of dumb. Like, that's not a lot. Right? So we left the effect size the same. Now remember, effect size is calculated by sample mean minus population mean divided by population standard deviation. So I'm getting the effect size by these numbers here. And we're going to go to y effect size in a second. But the larger the effect size, the easier it is to find, probably. Right? If I should care a lot, it probably means it's an easier thing to look for. Well, let's try it with 20 people instead. So if I have 80 and 120, sigma's 30, but now n is 20, that changes the standard error. So what that does, it doesn't change the effect size. It changes 6.71. It changes how far we have to go. So watch. If I have a z-score of 0 here, meaning that the population mean is 80, and we already said it's 1.64, if my standard error is 6.71 instead of 13, I don't have to go quite as far. All right, so I'm going to take 1.64 times 671 plus 80. And then we'll check my math. Now I only have to get to 91. We still have 120. Us, FE people. So the distance between 91 and 120 is going to be much larger. So then I would take my 91 minus my expected score, 120, and we're subtracting them because they're in this order. Okay. Divided by 6.71. Oh my gosh, this is going to give us a crazy z-score. 4.32. And it's negative. 4.32 is the very end of the distribution. It's going to basically tell us power is 1. But if I take my p-norm, put in 4.32. Yeah, 9999. So we have even more power. You don't ever round up and say 100%. There's like this weird stigma against saying power is 1, but let's check and make sure I did that math right. So I'm going to change my sample size only here from n is 5 to 20. Okay. Oh, my sample mean should be 120. Okay. Still lower tail's false because I still want a score that's higher. So I run all those, and then all this down here is the math that I was doing on the board. Yeah. Still math a little bit. So I got 999. But the purpose of that demo just there is to show you how much sample size matters. So sample size increases power. More people, more power. Why? Because standard error gets smaller. Because I have better precision. So the confidence interval is getting smaller. I can trust my mean a little better. And so it's easier for me to reject the null because the cutoff score kind of moves in. The z isn't changing, but since the standard error is changing, it's getting closer to the mean. Yeah.
Is that why like they're so hesitant of having these massive samples? Is because it's basically no standard error anymore?
Yes, but not the word hesitant. So most people use large samples because it gives you better precision, more like outliers matter less, and more power. But that's why you have to be skeptical if they have large samples and a very, very small effect size.
Yeah. Okay.
Okay. So let's switch back to 5. So this time change the effect size. So I'm going to change my sample mean, my expected sample mean. So I'm going to go back to 5 up here. So kind of back to the original numbers we had. Well, let's say I overestimated how different. So Power Rangers like increases your imagination scores, but maybe not that much. So only 20 points instead of, whoa, that would give me a crazy number. Instead of 40. Run the whole shebang again. This time I only have a 87% rejecting. Oops. So not so good. Right? I'm probably going to miss it. 80% is the criterion. That's way below 80%. We could even do one more. So I'm going to copy this line. But let's increase the sample size. So we've done kind of all 4. So I've lowered the effect size, and that clearly cut power in half. Right, so I cut the effect size in half, and that cut power in half. But now let's increase the sample size. So we might kind of get somewhere in the middle. Because 0.67 is a medium effect size. That's nothing to laugh at, right? Let's try it this time with 20 people. Oh, did I run that correctly? Oh, it went straight back to 90%. So effect size and sample size are the 2 largest components of power. Okay, that's what the demo is for. Clearly, the larger the sample, the more power. The larger the effect size, the more power. And that's this side. Okay. So I'm going to make you a list here of what affects power. But you can kind of play with the numbers. And the more different you make these, that's changing effect size. The more people you add, that's changing standard error. So they're affecting different components of your study. So we showed power things. So sample size, that's because it lowers standard error, which increases power. So more people, lower standard error, and increases power. The other one is effect size. So larger is more power. But I don't know that I have so much control over the effect size thing. Because what do I got to do to change that other than just a demo? Well, I got to figure out how to make my study more intense or somehow increase the difference between groups. And that may or may not be a feasible thing. Right? So I really have the most control over sample size. Sample size is like a quick and easy way to affect power. One of the other options that is not usually recommended is alpha. So power and alpha are opposites of each other, but clearly they're tied together. So a larger alpha is more power. And what does that mean? That means 0.10 has more power than 0.05. Because the larger the alpha score, the more we're moving it back towards the mean. So if I'm willing to make a mistake 10% of the time, I'm going to get more power to find it. So you can think of alpha as kind of like a leash. Right? And the shorter the leash, the harder it is to get away. Right? 5% leash is shorter than 10% leash. This is not really recommended. Don't do this. But it is true. Where are we on? 4? One-tailed versus two-tailed. We didn't talk about calculating a two-tailed test because it's a pain. So we just did one-tailed test. I'm going to give you a demo of what's happening. But a one-tailed test has more power. Most people also consider this cheating. But it does have more power. Because the cutoff score for one tail is 1.64 for 0.05. For two tails, 1.96. So we're closer to the mean. So it's less, our race car example, the finish line is closer. Increasing sample size or decreasing standard deviation, that's this one right here. So when I increase sample size, my distributions squish up because the standard error is getting smaller, which makes it easier to find the difference between the two. So these overlap a lot more than these. So it's decreasing standard error. Increasing the difference between the means, that's the effect size one. The larger the difference between the means, the easier it is to find. So this here, the overlap is a lot less here, which makes it more powerful than here. And then there's one more that they don't really talk about in the book, in this section. And I'll go ahead and add it as type of test. The only thing we've done so far is z-tests. So they haven't introduced this concept because you don't have any other options. But the statistical test type also affects power. So when we get to t-tests, we'll talk about that idea more. All right. And I think this is just the summary of everything. So larger sample size is more power. Alpha, a higher level, is more power. One tail is more. Decrease the standard deviation because of larger sample sizes, or increase the difference between means. That's kind of both effect size. So when you're asked, what are some things that you can do to increase power? This is the list that you pick from. Mostly, it's all about sample size. I have the most control here. I can run more people. 3 and 4 and a little bit of 5 are not things that people recommend because they consider it cheating. Okay. We don't call it cheating, we call it phishing. So you're phishing for results. I don't know. It's a thing.
So with 4, would you retroactively change it?
Well, 4 should really match the type of test that you're running. So if you're going to run a two-tail test, do two-tail power. I'm just that's way more complicated than it needs to be. One tail is easy to show you, kind of here's what's happening. If you're doing a one-tail test, clearly do a one-tail power analysis. So it should match step 1. What most people do with power, kind of getting to your question, That's actually the next slide too. So why would people care about power? And that's actually generally because they care about sample size. Since sample size is the thing we have the most control over. Oh, I know it's on this computer, right? No, because the guy has never fixed it. JK. So there's this cute program called G-Power that calculates power for folks. And I teach it in my upper level class. And the reason that we go over power so much is because I want to know how many people do I need to run. So I generally have a good idea of the type of test, the alpha and the 1 versus 2-tailed. We all do 2-tailed. So 3, 4, and 5 are set. Okay. This is the way that things are in our world. Okay. I would estimate effect size based on previous research or a pilot study. So I want to know how many people do I have to run for this test to get to 80%. So instead of calculating power, I tell it to calculate sample size. And it tells me how many people I need to run. That's really important for thesis projects, for students. I tell them this all the time. If you run this power analysis and it says you need 600 people, you might reconsider. You will be here forever. So it's usually a good way to estimate the number of folks you need in a study. So that's the sort of thing I do with this, is estimate sample based on setting power at 80%. All right, so that's why it's important, because you don't want to be looking for things that you're not going to be able to find. Now, what people do with all of this is all taken together, power, confidence intervals, and effect sizes, like all at once, are meta-analyses. So a meta-analysis is lots of studies at once. And so instead of taking one sample at a time, we're taking lots of samples. So some of you asked when we talked about the sampling distribution, when would you ever do that? You don't, but a meta-analysis is close. So I might take 20 different studies on the same topic, calculate their effect sizes, and look at how consistent an effect is. So each study is the data point, so each mean. So this is kind of like making my own sampling distribution. And so I don't know what the deal is with this book in like steps. It's really into like procedural steps. But you pick a topic, look at every study. Oh my God. We did one of these on judgments of learning. Do you know how many papers are on judgments of learning? Like 6 zillion. So we instead did every study that one research lab had done. We calculated their effect size for every component of their studies, and then make appropriate graphs, which looks like this. So this is just a couple of their studies. This is called a forest plot. You do not have to know that. But this line here is 0. And so each one of those bars represents an effect size and its confidence interval. So you can do confidence intervals on effect sizes too. And what we're trying to show is that over some of their studies, the effect sizes have changed. It's actually, they've gone down. So the ones on the top are the first studies. And then as we kind of come down here, these are the later studies. So their effect sizes have decreased over time. So we're either missing it, or they've changed their study in such a way that these are less powerful than these original studies. So this is called a forest plot. Okay. And so what people do with meta-analyses is they try to take, like, normally you're just reading one study at a time, right? Trying to take it and make a bigger picture. This is what this thing actually looks like. And they're really popular right now because people are trying to figure out why are effect sizes changing over time? Are we doing underpowered studies? Are we not replicating? Like, what is it? So back to that replication crisis idea. Okay.